Great, thank you. Thanks so much for the invitation and the introduction. It's a pleasure to be here. Happy birthday, Emmanuel. I'm going to be talking about how o-minimality can be used to answer a couple questions in Hodge theory, one old and the other newer. Sort of the interactions between o-minimality and Hodge theory is something that's seen sort of a lot of development in the past 20 years, and I think Emmanuel was one of the first people to sort of really get on board the train and realize the importance, and so he has many very influential papers in this area, all of which I've read. Okay, so I wanted to start off by talking a bit about the classical picture, which we already heard a little bit about in Mingju's talk yesterday. Let's talk about AG. AG starts off life as a complex analytic variety, upper half Siegel space modulo the symplectic group. And sort of first result in this direction is due to Satake in 56, who introduced a topological compactification of this space, which I'll call AG SBB. Sort of the underlying set is just AG together with the union of all smaller dimensional AGs. So starting with AG minus 1, then all the way down to the modular curve, and then A0, which is just a point. But with an interesting topology, and sort of that's kind of the point here. The topology is kind of was introduced as a way to sort of make sense of some results from reduction theory. And in the same paper, he suggests that it should have the structure of a complex analytic variety, and this was shown to be true by Baily in 58. In fact, he does more. He shows that this topological space canonically has the structure of an algebraic variety. And even better than that, it's sort of an algebraic variety that's very much connected to the theory of automorphic forms. So it's proj of a certain graded ring of automorphic forms. So I think this is the first place where the algebraic structure on AG shows up. This algebraic structure has some important sort of moduli theoretic properties. It's not literally a moduli space of sort of degenerating abelian varieties because there isn't a universal family. But the points can be interpreted in terms of one-parameter degenerations. So, yeah.
Did Baily define the structure by this Hodge, or he embedded the space into some projective space?
I think he shows it is the proj of this, yeah. Okay, so what is the modular interpretation? Well, like I said, it's in terms of sort of one parameter degeneration. So let's talk about over a curve. So suppose I have a family of abelian varieties over a curve. Okay, so my families are going to be Z, because X and Y are already taken. So I apologize for that, but there's nothing that can be done. So I have a smooth family of abelian varieties over a curve C. And suppose I close it up, perhaps by adding a point, into, let's say, a semi-stable family. And so there's a special fiber over, say, 0. It's called Z lower 0. We can consider sort of the Neuron model of this degeneration. And the limiting point with respect to this compactification is sort of the compact part of the Neuron model. Okay, so the limiting point is the compact part of, at least in the semi-stable case. neuron model. So in other words, usually the neuron model, some group scheme, it has a sort of a semi-abelian connected component, and we sort of throw out the torus part and just remember the compact abelian variety. That's an abelian variety of dimension anywhere between g and 0, and that's what the limiting point is. Third, there's we already see that here, but there's a natural polarization. Oh, this doesn't go up anymore. There's a natural polarization on this compactification. I mean, obviously by construction, it's the line bundle whose sections are interpreted as automorphic forms, but we can describe it maybe a little more geometrically. If we look at the universal family just over AG, geometrically, the natural line bundle that shows up is, well, we push forward relative one forms. That gives us a vector bundle. We take the determinant. And this is a line bundle. I'll call this L sub AG. And this line bundle is the line bundle whose sections with appropriate behavior at the boundary are the automorphic forms for which I get this ring. And in particular, it extends amply.
So in the case of semi-stable neuron model case, like what you explained, what is the natural extension coming from this line bundle to C? Is it
It's the determinant of the log forms.
Determinant of
the push forward of the log forms. With respect to the
boundary.
The boundary, correct. Yeah?
Okay.
Extends amply. Maybe I'll go over here now. What am I up to? 4. 4. It has a universal property, too. And the universal property is with respect to sort of families of abelian varieties on the complement of a log-smooth divisor. So let me write it down like this. I'll call this a universality. It says if x comma d is log-smooth, and suppose I have a family on the complement, so x minus d maps to AG, and I want to understand how it closes up inside of this compactification. The answer is it does. So I get an extension here. And moreover, it's compatible with this natural line bundle. So the pullback of this, maybe I should say it extends amply. Let me give it a name, to LAGSBB, which is slightly cumbersome. But that extension of that ample extension of the line bundle pulls back to the natural extension here. Equals, I'll call it LX. So again, what this means is I take L where I actually have the family of abelian varieties, and there's a natural extension to X, either via taking a semi-stable model and taking the determinant of log one forms, or as we'll see, sort of there's a more canonical way to, there's a different way to describe this canonical extension purely using Hodge theory. So if you're familiar with that, then this is just the Hodge theoretic extension. So I should put a little warning here. So this really needs to be the stack for this. Okay, so I need an actual family of abelian varieties over x minus d. So when I write this map in this context, I really want a map to the stack. And that's going to be sort of a recurring feature whenever I talk about this universality property. So just keep that in mind. And a related issue is that here, if you really want to be careful, there should be a power for similar reasons and for some other unsimilar reasons. But again, whenever I write this sort of universality property, you should understand it as either sort of compatibility with respect to a Q-line bundle extension or up to taking some appropriate power. Okay, and this is due to Borel in 72. And actually, related to this, there's a version in the analytic category with respect to polydisks. Okay, so I'll call that 4 prime, which is even this same property, even for x comma d, the polydisk, with respect to, with the log smooth divisor being the coordinate hyperplanes.
So log smooth refers to normal crossing divisor, or more generally logarithmic structure like Kato?
I mean log smooth in the pedestrian sense at the moment. So yes, just a smooth thing with a log smooth divisor. But it may well also hold for smooth objects in the log category. But someone will have to tell me that. Okay, so it holds for this pair in the analytic category, meaning if I have an analytic map to AG, then it extends analytically to the polydisk in such a way that the line bundle canonically pulls back. Okay, so this was all for AG, and Satake did the sort of general case of this kind of topological compactification shortly thereafter in 60. And then Baily and Borel together proved the analog of 1, I guess 1. In other words, realizing that compactification as a projective variety given by Proj of a graded ring of automorphic forms in 66.
This is now for more general Shimura variety.
Sorry?
This is for what? For which?
Yeah, this is for any Shimura variety. So these two together did sort of 0 plus 1 for Shimura varieties.
Historically, I think the Lin systematized the notion of Shimura varieties, so people did not know what. I'm not sure exactly what when Shimura, the word Shimura varieties is based on works. I don't know, it works. Of course, Shimura wrote papers in the 60s, but then the Lin explained what things. I don't know the history, but I don't think people know the word Shimura varieties in the.
Yeah, so yeah, this is certainly not well. Okay. It's not necessarily a complete history, but yes, indeed. I mean, in order for people to even talk about this, I believe Delin's work sort of systematizing Shimura varieties was important. And I also heard someone say something about locally symmetric varieties. Oh, I see. Yes. Okay. So Emmanuel is suggesting instead of saying Shimura, I say sort of arithmetic locally symmetric. Okay. Yes, agreed. Because the whole story I'm giving right now is over C. And now that I've said arithmetic locally symmetric, I should mention that it's sort of Mach who did the same thing for non-arithmetic locally symmetric varieties.
Non-arithmetic. Who did?
Sorry?
Who did for non-arithmetic?
Mach. Yeah. Okay. Great. Okay. All right, so now that's all the history. So again, in this sort of around the same time period is when Griffiths was developing sort of the abstract notion of a variation of Hodge structure. So suppose xd is again log smooth. And suppose we have a polarizable integral variation of Hodge structure. I'll just say a z variation of Hodge structure on the complement. So if you like, sort of you can keep in mind the geometric case. Maybe even we have a family z circle over. So let me just call this x circle from now on. So this is a smooth projective family, and I can consider the variation of Hodge structure underlying the local system of the kth cohomologies of the fibers. So sort of take V to be R, I don't know, K pi naught lower star. This Z is an unfortunate product of using Z for my family, but again, it's unavoidable. Okay, and so again, this carries the structure of a variation of Hodge structure, meaning in particular that there's a filtration of the associated flat vector bundle. So let's say, well, I guess that's in the general case. So FP V on the associated flat vector bundle. O tensor, we call this VZ. So it's the interval local system. And this leads to a period map from x naught into some period domain parameterizing polarized Hodge structures modulo a group gamma containing the image in the monodromy representation. I completely forgot to say, I knew there was a reason I left this title up. This is all joint with Stefano Filipazzi, Mirko, Mauri, and Jacob Tsimerman. Okay, good. So I'll leave that now. And sort of in analogy with this, the way this story plays out for AG, Griffiths asked, well, first he showed that in fact this is always a compactifiable morphism. So in other words, the closure of the image makes sense as a complex analytic subvariety. Because this is naturally a complex analytic variety, so this is due to Griffiths. Okay, so we get a factorization of this map. This is really living in the analytic category. And Griffiths asked, well, is this curly Y algebraic? So Griffiths, and he asked this in his paper from 70, is curly Y, and also the map to curly Y and psi algebraic? Question. Even better than that, he asked, well, there's a natural line bundle which for curvature reasons should be ample. So he asked if is this line bundle, which you get by just tensoring the determinants of all the Hodge filtration pieces together, ample. And finally, he suggested that one very natural way to address both of these questions is via showing that there is a compactification of curly Y as proj of some graded ring of sections of this line bundle of sort of reasonable growth at infinity. Would be to construct sort of a curly Y Baily Borel from as sort of a proj of a ring of sections of this line bundle to powers where we don't want to take all sections because that would be a mess, sort of reasonable ones, whatever that means. So there's a natural Hodge metric lying around. You could look at ones that have reasonable growth with respect to that metric. Okay. So a number of years ago, using some techniques from o-minimality, and together with Johan Brunebarb, we sort of answered these two without using this compactification. That was sort of the key input of o-minimality, allowing you to produce algebraization theorems that didn't involve a compactification. So I'll come back to that in a second, but curly Y is indeed algebraic, the analytification of some algebraic variety, as is psi, so I don't know, the analytification of some map, and this is algebraic and ample. So L curly Y is Ly, analytic, ample. Okay, so that leaves open the question, well, is this, is it actually true that you can construct a canonical compactification of the image of, or the closure of the image of the period map as a proj of a sort of ring of things that are like automorphic forms in this much more general setting? And the answer is yes. So that's the first theorem that I want to talk about today. So this is with Filipazzi, Mauri, and Jacob. So we can consider the ring of sections. Well, it's much easier to say what we mean by this now that Y has an algebraic structure. We can look at moderate growth sections, sections that have subpolynomial growth, with respect to whose norm has subpolynomial growth. So we can look at this ring. First of all, this is finally generated. And proj, which is then a projective algebraic variety, is a compactification of Y. And if we define the Baily Borel compactification as just being proj of this ring, it's a compactification of Y satisfying for which this line bundle, which is called the Griffiths bundle, extends amply and universally in that sense, such that Ly extends amply and universally, as in 4. And in fact, even 4 prime. So even the analytic version of this with respect to polydisks also holds.
I'm sorry, can I ask a question?
Yeah, please.
So I don't really understand the Y here. The Y was already compact to start with?
No.
Because it was, and now down here.
No, this is not compact.
But you put a bar here.
Yeah, it's a closure in here.
That's a closure in here.
Yeah.
So now it is for more general period domains which are not Shimura variety.
Yes, this is just a general period domain. And,
Okay, so I saw that you take R1 Philo, so what is R anything?
No, that's a K. Yeah. K, not necessarily equal. Well, it could be, but it's a K. It's an integer. And 4 prime as well. Okay, great. Sorry, is another question? This property. Yeah. The analog of this property. So it means it's in the log smooth case, there's an extension of the map which is compatible with the line bundle. Yep. And the same thing for 4 prime. Okay. Let me make some remarks. So I wrote down a bunch of properties of Baily Borel. We have 4 and 4 prime here. The fact that it's proj of this finitely generated ring is sort of the analog of this 1 here. So we've sort of also ticked off property 1. What about the other properties? I guess 3 as well, right? It has a natural polarization, namely the extension of this Griffiths bundle. So remarks. So first of all, there's a natural analog of 0, which is that there is indeed a stratification of this Baily Borel compactification by varieties that admit finite period maps. Okay, so YBB is a disjoint union of subvarieties, locally closed subvarieties with sort of finite period maps. You might ask, what are those period maps? Well, they're the natural ones, and so this leads me to the analog of 2. the sort of modular interpretation, at least with respect to taking limits along one parameter families. And sort of up to this finite ambiguity, the points in this compactification are recording the associated graded of the limit mixed Hodge structure. Okay, so 2 is these are the period maps for associated graded of the limit mixed Hodge structure. Just subpolynomial with respect. So the Hodge norm is less than polynomial in norms of some choice of algebraic coordinate functions.
No, but in the case of the classical modular form, so the codimension 1 complement, so certainly you want to not to have, to have something which is, you want to exclude things which have a pole at infinity.
Yes.
So if you have a growth.
So its growth will look like a monomial in logs of norms of coordinates, algebraic coordinates. Yep, it'll have a logarithmic growth with respect to the algebraic coordinates of the limit mixed Hodge structures. And indeed, this is the Hodge theoretic spin on what I described here, because in the case of families of abelian varieties, the limit mixed Hodge structure has a sort of weight 1 piece that is not degenerating. That gives you the compact part of the neuron model, the semi-stable neuron model. And then it'll have some weight 0 and 2 stuff, which is entirely Hodge-Tate, so it records no information. So it doesn't sort of help, it doesn't in particular give us positive dimensional variation in the boundary. Finally, I should say, so there's been some previous work on this question of sort of building Baily Borel type compactifications by Green, Griffiths, Laza, and Robles. And also a separate paper by Green, Griffiths, Robles, where they treat some special cases, in particular the case when x has dimension 2, so some special cases, e.g. dim x2. In particular, this the second paper, this Green, Griffiths, Robles paper, proves something that's an important ingredient in the proof of the general statement, plus GGR prove important ingredient. Okay, so this is useful for a number of reasons. From the perspective of sort of moduli theory, it essentially provides a canonical compactification to any moduli space of varieties admitting a local Torelli. So that includes sufficiently large degree hypersurfaces. That includes sort of Calabi Yau varieties. I'm going to go on a tangent now, which, if you're interested only in Hodge theory, might seem uninteresting, but actually it will be interesting, and it won't be a tangent. So bear with me for a second. So in some sense, from the perspective of geometry, this Griffiths bundle, where I tensor the determinants of all the, this tensor of the determinants of all the Hodge filtration pieces is kind of natural from the perspective of Hodge theory, because it'll sort of see the variation in every filtration piece. But from the perspective of geometry, there's a more natural candidate for what line bundle should polarize your moduli space. So again, suppose I have some family like this, and suppose it's a smooth projective family of n-dimensional varieties, and often the variation of Hodge structure I want to take is middle cohomology. And often it's not the Griffiths bundle which shows up geometrically, it's the deepest part of the Hodge filtration here. So the deepest part of this is just the push forward of the canonical bundle of x naught over z naught. This is called the sort of Hodge bundle. In particular, if we have a family of Calabi Yau, a smooth Calabi Yau varieties, then this is already a line bundle. So if it's a family of sort of Calabi Yau varieties, already a line bundle. Well, so I'll call that M to distinguish it from L, which is the tensor of the determinants of all the. Again, this is in the case when it's already a line bundle. Okay, so this is a semi-positive line bundle. So you might ask, okay, well, what about its sort of semiampleness properties? So that leads me to the second theorem. Theorem 2 is suppose x comma d is log smooth, and v is a polarizable integral variation of Hodge structure, which looks like it comes from a family of Calabi Yaus, meaning it's the deepest part of its Hodge filtration is one-dimensional. So I'll just call that a Calabi Yau variation. Parenthetically, that means that the deepest filtration piece is a line bundle, which I'll just call MX, or MX circle. Okay? So the theorem is almost that MX is semiample, which again, I should have observed sort of a large, at least a corollary of this theorem is that in the log smooth setting, the natural extension of this Griffiths bundle, Lx, is semiample. So its ring of sections is finitely generated. And proj of it will return the normalization of this YBB. Maybe not literally the YBB, because there's also some, if the image is not normal, this is actually giving a compactification of the image as opposed to the proj of the section ring on some log smooth thing, which would always be normal. But anyway, that's kind of a technicality. Assume that this line bundle, this Hodge bundle, is two conditions. It's integrable, so I'll define what these mean in a second. And 2 has torsion combinatorial monodromy. Sorry? I haven't said what these mean, but I will. I promise you. So yes, I'm just saying it's integrable. So this is just a word at the moment, but I'll tell you what it means in a second. It's meant to, it's called that for a reason, but I'll get to it in a second. It's integrable and has torsion combinatorial monodromy. Then it's semiample. Okay, so that's kind of cool because that means that there's 2 up to this normalization business that I mentioned, which is actually one of the sort of more delicate parts of the paper. There's sort of 2 Baily Borel compactifications, depending on whether you want the Griffiths bundle to extend amply and universally, or whether you want this Hodge bundle to extend amply and universally. It's the deepest part. It's the deepest part of the Hodge filtration, which I'm assuming is a line bundle. Yeah, does that make sense?
Yeah, just you written MX0.
Oh yeah, sorry. So yeah. So in the context of Hodge theory, there's always kind of a preferred extension. You basically take the Deligne extension of the local system it sits inside, and then as a consequence of the nilpotent-orbit theorem, it extends algebraically. Okay. But yes, so yeah, that's a good point. Somehow the Hodge theory gives you this canonical extension that we're kind of using everywhere that in geometry is a little harder to see, but roughly speaking, you sort of go to a semi-stable model and do some logarithmic thing, and that's giving you the sort of, in geometry, the preferred extension.
What's a semiample?
There are global sections. For every point, there's a global section that's not 0 at that point. So there's a map you get by taking a proj of the global sections for a sufficiently high power. In other words, the section ring is finitely generated and gives a map. Blah, 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 blah. I lost my place. Oh, yeah, great. OK, so we have these two conditions. X is proper here, yes. Yes. Well, it's still true if it's not proper, but the interesting case is when it's proper. You can still talk about semiampleness in the non-proper case, but then you have to use the non-vanishing sections definition. Or rather, semiample. Well, anyway, yeah. OK, so theorem 3 is that these two conditions are satisfied whenever you're looking at middle cohomology for a family of Calabi Yaus. So star plus star star hold whenever V is middle cohomology of a family of Calabi Yaus. OK, so the reason this looks like a tangent, but it's not. I'll get to that in a second. But I also wanted to sort of go on this brief walk in the garden because I wanted to mention a corollary, which is sort of an important result for sort of the minimal model program, which is this theorem 3, together with theorem 2, resolves the b-semiampleness conjecture. So this corollary is the b-semiampleness conjecture of Prokhorov and Shokurov from 2009. OK, so I don't think this is an MMP heavy crowd, so let me keep this brief. But let me just say what the pieces are. So if we have a pair, which it has sort of the singularity is allowed in the minimal model program, so it's LC. And suppose we have some morphism, which is k-trivial, in the sense that the sort of log canonical divisor here, which is kz plus delta, is pulled back. So in other words, kz plus delta is linearly equivalent to something pulled back from pi. So this is the setting in which we have what's called the canonical bundle formula, which decomposes this canonical bundle into 3 pieces. Okay, the canonical bundle downstairs, plus a boundary part, plus a moduli part. Okay, so you might secretly be familiar with this because this sort of is what shows up in Kodaira's work on sort of minimal elliptic surfaces. The point being, if you have some elliptic surface with some degenerations, I don't know, maybe I have some degenerations like this. So Kodaira interprets, in terms of kind of the global geometry of the surface, sort of how many singularities are allowed, because every type of singularity contributes a certain understandable thing to this boundary part. And the moduli part is just sort of the degree of the map to the J-line given by the generic part of this family. So somehow this canonical bundle formula in the case of elliptic surfaces is controlling in terms of the global geometry both the variation of Hodge structures on the generic part and the singular fibers that show up. And this is sort of a higher dimensional generalization of that. OK, great. So now I can tell you what those two conditions are. I should say there's a lot of work that past work on the b-semiampleness conjecture that I'll at least mention some names while I'm erasing, I guess. So, I mean, this goes back to sort of work of Kodaira, and then also Kawamata and Fujino, and then Kolar, and who am I forgetting? And then more recently, Ambro, Flores, and Lazic. Okay, so what are these two conditions? Well, this integrability condition says the following. So again, we're in the setting of theorem 2. So we have, let's say, a proper log smooth x comma d, and we have a Calabi Yau variation on the open part. So the integrability condition says that, well, whenever you have some s mapping into x, which may land in the boundary, and indeed that's kind of the important case, if this Hodge bundle, when pulled back, is not big, so this is S irreducible. If the pullback of mx not big, then the content is going to be some part of the variation is trivial, at least on some dimensional component of this variety. So to say it precisely, there is a piece of the variation. There is a piece of the variation. So the condition is that whenever this happens, there is a piece of the variation whose period map is not generically immersive. The variation it has generically immersive period map. Okay, and then this is to rule out there being parts of S for which the variation of Hodge, like transcendental curves inside of S along which the variation is trivial, but not algebraic curves along which it's trivial. Because this not being big tells you in some sense that there are transcendental leaves along which the variation is trivial. And the fact that there's an actual piece of the variation which has non-generically immersive. There's a piece has non-generically immersive. Sorry, you want to know that there's a piece of the variation which is isotrivial along algebraic curves, right? And that's what having a non-generically immersive period map would do, because the image of the period map is algebraic, right? So if it's non-generically immersive, that means the period map has a generic fiber. So that gives you an actual curve through the generic point along which this piece of the variation is isotrivial. Okay, and the second condition is a little easier to understand. It's simply the following.
What does integrable actually mean then? Sorry. So which here was the definition of integral?
So we say the Hodge bundle is integrable if, whenever you have a map from an irreducible thing for which this pullback is not big, then there is a piece of the variation which has a non-generically immersive period. But again, that's yeah. Sorry. So the
compactification, you mean? You compactify it, and then you mean that you compactify everything. You assume the line bundle is not big, in the sense that the sections of powers are not. What does it mean big? It means
it just means the global sections don't grow as grow less than sort of a power of the dimension.
Normal compactification of S.
Yeah. So here, this is compact, and X is proper.
Okay.
So we're talking. Yeah. So I see the question now. So everybody's proper here, but importantly, we're letting S go into the boundary. So when I say a piece of the variation, I'm implicitly saying associated gradeds. Some piece of the associated graded variation has non-generically immersive period map. Okay, so this is the bit. Perhaps I made the mistake of stating it both not precisely enough and too precisely. But the idea here is that if this thing is not big, then through a generic point, there's some piece of the variation. Through a generic point, there's an actual curve along which some part of the variation is trivial. Okay, so I can find some algebraic curve along which something is trivial. Okay, because the danger here is that this might not be big, but it's only trivial along sort of transcendental stuff. And to build something on which the mx descends amply, it had better be the case that sort of whenever there's a transcendental thing along which it's algebraic, along which it's trivial, it's actually contained in an algebraic thing along which it's trivial. Okay, anyway, sorry. Let me say the second condition. This combinatorial torsion monodromy, like I said, it's in some sense like a combinatorial version of this, but it's easier to say. I'll just draw a picture. Whenever there's a nodal curve mapping into X, for which the pullback of this Hodge bundle is numerically trivial, so such that the pullback of this is numerically trivial, then it's actually torsion. Okay? And indeed, I mean, this is, both of these are clearly necessary, but this is maybe the one that's easier to understand. If there's going to be, if it's semiample, that means there's a map for which the line bundle is pulled back and it descends amply on the target. So if that's the case, then anything along which it's numerically trivial has to live in a fiber of that map, in which case some power of it has to actually be trivial. Right? It can't be some non-torsion degree 0 line bundle. Okay? And the reason this is called combinatorial monodromy is because Hodge theory tells you on each component it's torsion, but you don't know about these kind of combinatorial loops that show up. Well, you're kind of integrating the pieces. You want to integrate a foliation. You want to algebraically integrate a foliation along which it's trivial, basically, that's the point. So yeah, it's a statement about the algebraic integrability of that foliation. Okay, so let me get to some ideas of the proof, but let me first kind of close the loop on this tangent. The reason I mentioned this kind of theorem 2, which seems worse because it requires some conditions. In fact, the proof of theorem 1 lives in the world of Calabi Yau variations. It's kind of very important to the proof, and it goes via theorem 2. Okay, so at least up to sort of this normalization business that I mentioned. So theorem 2, in fact, implies theorem 1 up to sort of normalizing y. Okay. And why is that? Well, it's because to any variation, I can associate a Calabi Yau variation for which the Griffiths bundle is the Hodge bundle. Okay, so here's the construction. It's very easy. The key point is that the Griffiths bundle, L, which is the tensor of all the determinants of the filtration, is the M, meaning the Hodge bundle, meaning the deepest part of the filtration of, you just take the determinant, you take the tensor of the appropriate wedge of the variation, right? So if I take the, for each p, if I take the rank fpth wedge of v, this will be a Calabi Yau variation whose deepest piece is the determinant of fp. So that if I tensor them all together, this will be a Calabi Yau variation whose deepest piece is the tensor of the determinants of all the fp's. And star is automatic for the Griffiths bundle. And this brings me to the work of Green, Griffiths, and Robles. What they prove is that the Griffiths bundle, viewed in this light, satisfies condition 2 star. This is the theorem of GGR. Okay, so both of these conditions are satisfied in the case of theorem 1. Okay, and the first is automatic, like I said, and the second requires proof. Okay, great. So now I want to spend the last few minutes discussing some ideas from the proof. Let me put this up there. And actually, maybe I'll erase this one and keep the other theorem on the board. just so we can see it for now. Okay, so here's the idea of the proof of theorem 2. Okay, so we're giving ourselves a proper log smooth x comma d. And we're giving ourselves a Calabi Yau variation that satisfies these two properties. Star and double star. Okay, great. So what is the first step? Well, somehow the philosophy here is it's much easier to check that a line bundle is ample than it is semi-ample, because ampleness can be numerically checked by Nakai-Moishe zone. Semi-ampleness is much trickier because a line bundle might be trivial on a subvariety but not on the first order thickening. So there might be some infinitesimal obstructions. So the strategy of the proof is to produce the variety that x will map to, for which the line bundle will descend and be ample. Okay, so we want to produce this quotient map. Okay, so we make that quotient map. So I'll use an even different font. I used curly y for an analytic y before. I'm going to use some kind of different font y for just a topological space. Sort of the topological quotient. This is the topological quotient that should be, this whatever extra curly y should be the space underlying this the proj of the section ring in the case of theorem 2. So we know what it has to be, right? I mean, what are the if this is proj of the section ring of the Hodge bundle upstairs, then we have no choice but to contract all curves that the line bundle is degree 0 on, right? So this curly y must be x mod r, where r is the algebraic relation given by connectability by chains of degree 0 curves. Connected by chains of degree 0 curves. Okay, and a priori, for each particular, if you bound the length of the chains and the degree of the curves, that's sort of a finite type family. But a priori, these chains could get infinitely long. So it's not even clear that this is kind of a reasonable topological space. Okay, so you have to prove that. So the lemma is that this is in fact an algebraic equivalence relation. So lemma R is algebraic. And if it's algebraic, then it gives you a reasonable topological space, in particular a Hausdorff topological space. Okay, great. So the topology is good. And if the topology is good, well, with a little more work, if you blow up x enough, you can show that sort of the natural stratification you have coming from the log smooth divisor kind of descends to a reasonable stratification down here. So blow up x so that Q respects stratifications. In which case, the results with Brunobarb that I mentioned at the very beginning tells you that at least on strata, the strata down here are algebraic and the line bundle descends amply. Okay, so mx descends amply on strata. So the whole difficult part is sort of gluing these different strata together. This is by the theorem I mentioned at the beginning, and also using these two conditions. This is sort of the most important place where these two conditions show up. Let me go over here.
already knew that y was this.
Yeah, that's right. So y being algebraic. So this is just the straight up the closure of the image of the period map. Yeah. So the point is, and this is what I'm about to say, that once you do these blow-ups, each stratum is the image of some period map, which you then know is algebraic. And then you want to kind of glue all these things together. That's the tricky part. Okay, I don't have that much time left, but let me try to finish. Step 2. Okay, let me draw a pic. Let me kind of do this in the form of a picture. So here's x. Okay, and this is going to be my curly y. Okay, and there's some log smooth divisor in x, so there's some kind of stratification of x. So let's say x1 is kind of the smooth part of the divisor, and then there's a deeper part of the stratification where two divisors intersect, and so on and so forth. Okay, and we know that under this quotient map, the stratification kind of behaves well. So downstairs you get something that looks like this, where this is, so I have an open part first of all. I have a curly y1 and a curly y2. Okay, and the step 2, and I won't get into the details here at all, is to use Hodge theory. Do I have a different color? Yes. So what do we want to do? We want to produce, in order to algebraize this, we want to produce sections of the Hodge bundle upstairs that separate fibers of this map. Okay? And so step 2 is we're going to use Hodge theory to show that for any one of these strata, you can find sort of a neighborhood of that stratum, such that in the inverse image, which kind of looks like this, you have sections which separate fibers on the stratum. Okay? So let me write that. Or maybe I won't write that, because step 3 is the one I want to get to. So let me just say it again. So we want to, you use some Hodge theory, and there's this is in some sense the heart of the, well, this is one of the two hearts of the proof. So for each stratum, you want to show that there's a neighborhood such that on the inverse image, this kind of tube-like thing, there are sections of the line bundle which separate the fibers on that stratum. Okay? And you're going to do that for every stratum. So also here, you'll have sections in this neighborhood which separate points on that stratum. Okay? So that's already something. But that's not even enough to get an analytic structure down here. Okay? And I'll tell you the problem. The problem is that I have sections in a neighborhood here of the inverse image which separate fibers above this stratum, but I have no idea what it does off of this stratum. Okay? Now, to get the sections that separate the fibers on this stratum, I have to work locally on this stratum. So I don't know that the sections that exist locally along curly y1 can be kind of put together in a full neighborhood of curly y2 to get sections that separate the fibers on this bigger stratum. Okay? And I mean, this picture is simple, but we know that from experience with Baily Borel compactifications of AG that the topology here is extremely complicated. So this is a stumbling point. Okay, but that's where o-minimal GAGA comes in. Let me just, maybe because I'm already over time, let me just describe in words. So notice in the first stratum, we don't have a problem, because this result of with Brunebarb that I mentioned, it's in fact a little stronger. It tells you that there are global sections, global algebraic sections of the line bundle which separate points on curly y0. Okay? Now, global algebraic sections live on Zariski opens, which in particular include a full neighborhood of any point in curly y1. Okay? So the fact that I have algebraic sections of curly y0 separating fibers out here, plus the local ones I have here, actually is enough to give me an analytic structure on curly y1 plus curly y0. Okay? So this theorem, which actually is better than telling you locally here you have the sections. You have them algebraically, so on Zariski opens, tells you that have algebraic sections. Sorry, I know I'm going over, but it'll be done soon. Have algebraic sections separating points of curly y naught. So that means that curly y bigger than or equal to 1, sorry, less than or equal to 1, in other words, the union of this and this, has an analytic structure. Well, actually, it has a definable analytic structure, because I lied to you. The open neighborhoods on which I can construct these Hodge theoretic sections are on a definable cover of curly y1. So this is a definable analytic space. OK, and so now by o-minimal GAGA, and so this is sort of the key point, o-minimal GAGA, which was also proven in the same paper with Bruna Barb, allows you to algebraize maps even in the non-proper case. So this is very much a non-proper image of an algebraic variety. But it lives in the definable analytic category. So therefore, curly y is algebraic. OK, and now you can sort of cycle. Now this is algebraic. So you can use the results of the first paper to construct algebraic sections which separate fibers on this open. Now that's in a Zariski open, so it's a much bigger neighborhood. And that's enough to give me sections that separate fibers in this neighborhood away from this point. Then combined with these sections, allow me to add the next deepest stratum. That has a definable analytic structure, blah, 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 so on and so forth. OK, sorry, I'm already over. So I'm just going to stop there.
Thank you very much. Are there any questions?
I think I missed where you said that you were passing to normalization, or exactly why you were passing to normalization. Could you just...
Yeah, sure. So everything I described was the proof of semiampleness. So if you show it's semiample, so in particular, you produce this quotient space. In particular, the fibers are connected. Okay, so the algebraic structure you put here is really the is really the sort of Stein factorization of the map you eventually want to do in the case of theorem 1. Okay, so now you've produced an algebraic structure on what will be the normalization of the thing you want to make. So now you have to do some additional finite descent, and okay, well you use something very similar to this, but it's a little more complicated because, you know, it's using Hodge theory, it's easier to sort of glue things along connected families than along sort of discrete families. So you have to work a little harder. I don't know if that answers your question, but
I guess maybe just in the original sort of o-minimal GAGA paper, you really produce an algebraic period image without passing to normalization.
Correct. Yeah, and we do that here. I just haven't described the proof, that part of the proof to you. So this is
Compactification on the true period image.
Correct. Yeah. So in the case of theorem 1, I mean, somehow we know that these sections separate points of the actual image, and so this will be a compactification of the actual image. In the case of theorem 2, we do not get that, and that's kind of a subtle point. I can tell you more about it. It's related to the fact that the limit mixed Hodge structure is polarizable. But the polarization involves the local monodromy, so it does not glue sort of combinatorially. If I take two divisors that are coming together, the polarization here depends on this local monodromy, the polarization here depends on this local monodromy. The polarizations don't glue. So on the strata for which, on strata that I should contract under this map, you might not have an actual polarizable variation of Hodge structure without doing some more work. It's like an unpolarized variation of Hodge structure for which this map should be the period map. And in the case of theorem 1, you can actually concoct a polarized. You can get rid of that ambiguity. You can actually produce a polarizable variation of Hodge structure on this sort of chain of stuff. And in the case of theorem 2, we just don't know.
One more question. One thing I've never quite understood is, with regards to using o-minimality for these kinds of things, how much more sort of o-minimal input you need beyond the statement that a global period map lands in a finite union of Siegel sets. Like if I was just given that statement itself, Would it be possible to use sort of more traditional techniques to recover the same sort of results, or you really need the o-minimal machinery?
Well, I mean, that in some sense would be enough, but you'd end up reproving sort of o-minimal GAGA along the way in order to prove things. So, I mean, the real reason, so the most important, and there's many ways o-minimality shows up. One of the most important ways is this step here, where we use the fact that a definable analytic space, which is the image of a proper map from an algebraic variety, is algebraic, okay? And that goes via sort of Artin's theorems. And the kind of the most salient point of that proof is algebraizing the thickenings, the Artinian thickenings you get sort of on the exceptional locus. And for that, you really need the power of sort of the definable analytic category, because you need to be talking about the sheaves. Yeah.
So in the end, you explain the algebraic structure on this quotient. So I understand you construct it topologically. And then you say that you have some sections of your line bundle, but I didn't. So suppose I didn't quite understand the logic. So you have in BBT you get algebraic sections on the full open. But are those sections have a pole at y1 or not?
Are they what?
Do they have poles along y1?
No. They're actually global sections on X. So they might have zeros on the deeper strata. But they are global sections. Yes. But so it's kind of in the iterated step, the step where I go back, yes. You construct sections of the line bundle, global sections, yes. which separate points on this now bigger thing that you've just algebraized. So you're constructing more sections now because now you're including y1.
And how do you know this? By using your BBT paper.
Yeah, that's right. So once it's algebraic, now you can use some cohomological machinery in algebraic geometry to show that you can produce global sections which might have zeros on the deeper strata, but are non-zero on y less than
global. Okay.
Yeah.
And what was the remark about non-polarizable Hodge structure? How do you get it here?
Yeah, I mean, you can already see this. So if you look at this is kind of in some sense a baby case, but it's also an important case. If you look at the Hilbert modular surface, sort of the log smooth compactification at the cusp is some cycle of curves. Okay, and so the associated gradient of the limit mixed Hodge structure is very simple because it's entirely Hodge-Tate. But sort of the polarization form you get here uses the local monodromy, and if you compute the sort of the monodromy of that local system you get, it's actually the multiplication by the real units. So it has infinite monodromy there. So that's an example of when you get non-torsion combinatorial monodromy. And similarly, it shows you that the limit mixed Hodge structures, they glue together as a variation of Hodge structures, but not as a polarizable one, because that's infinite monodromy.
And this is not a case of your thing, this Hilbert.
Yeah, that's in fact why it's important to go via the Calabi Yau construction, because if you take determinant here, it's finite, which is kind of magic in this case, but somehow the proof explains that when you reduce to the case of only caring about a one-dimensional part of the Hodge filtration, that you automatically get torsion.
Okay, so thank you again.